Okay, so in the previous class, I started with a concept of eigen sequence, okay, of a linear time invariant or linear shift invariant system. This was that page. Hn represents the unit sample response of a linear shift invariant system. My claim is, if I give a sequence of the form a to the power n, then the corresponding yn will be of the same form e to the power n, just amplitude will change, which means give this, you will get the same thing at the output with the changed amplitude. This is like a matrix eigenvalue eigenvector problem, where if a matrix has an eigenvector say x, then the matrix times x will come back as x only multiplied by a scalar constant lambda. All the elements of x get multiplied by lambda. Similarly, a to the power n, if I input, output will be a to the power n, but every sample of a to the power n for each n will be multiplied by the same constant, some constant, you can call it lambda. Why? Because we showed that if you carry out the convolution between yn, between hn and xn, because the output is convolution between x and h and equivalently h and x. But I told you in the beginning, I always prefer convolution between h and x, this format, because then derivation becomes easier. It is what I have found, over years. So, I always prefer this. So, if you know hr, this means hr x n minus r, summation r minus infinity infinity. Now, x of n is a to the power n. So, x of n minus r is a to the power n minus r. And now, this is coming in the power, n and r, they are coming in the power, and this is separable easily. A to the power n minus r is a to the power n into a to the power minus r. A to the power n can go outside, because it does not, the summation is over r. So, this a to the power n does not depend on r. So, it can be taken as a common, it can be pushed outside. Inside you have got this summation h r a to the power minus r. This is a summation, r is a local index 0, 1, 2, minus 1, minus 2, all that, and you get a constant independent of n, independent of index n. Okay, there is no index n here, it is a constant, it is true for every n. You can give it a name lambda as a function of a, because a is your choice. So, this value will change from in accordance with a. If a changes, this overall value will change. So, it is a function of a. So, I call it lambda a. It is like an eigenvalue. So, if you give a to the power n as input, you get lambda a into a to the power n as the output. What is the advantage of this? That suppose I have got one sequence, some constant a 1 to the power n, and if I input it, it gives me an output a 1 to the power n only, but multiplied by some constant, some eigenvalue lambda a 1 of this form. That is, in this summation, instead of a, you put a 1, whatever you get, lambda a 1. Similarly, a 2 to the power n, if I input, I know from this I will get output lambda a 2 to the power n. What is lambda a 2? Here instead of a, put a 2. Then if I give neither this nor this, but a linear combination of them as a sequence, that is, this a 1 to the power n is a sequence, every sample multiplied by c 1, a 2 to the power n is a sequence, every sample multiplied by c 2, and these two are added, you get a resulting sequence. If I give this combination at the input, to calculate output, ordinarily I would be requiring convolution. That is, I have to carry out a convolution between h n and this total thing. But since system is linear and shift invariant, system is linear, this operator t, that is the system working on a summation, will be same as summation of individual responses, that is, summation of response due to this part and summation of response due to this part. Response due to this part t working on c 1 a 1 to the power n, because of linearity c 1 is a constant, so c 1 will go out, t will work directly on the sequence, this response multiplied by c 1, and again c 2 into a to the power n, t working on that. So, c 2 is a constant, because of linearity c 2 will be pushed out, it is same as t working on a to the power n first, then multiplied by c 2, and these two are added. But I know what is t working on a 1 to the power n. If a 1 to the power n is input, what is output? T a 1 to the power n, I do not have to carry out any convolution. I can straight away write in terms of eigen function, because this is eigen sequence a 1 to the power n. So, I know it will come back as it is a 1 to the power n, just multiplied by a eigen value, that is scalar constant lambda a 1. Similarly, t of a to the power n, I do not have to calculate. It will be same as a 2 to the power n, because this is an eigen sequence. Just the amplitude will change, it will be lambda a 2. So, calculating the output becomes damn easy. I don't have to carry out any convolution sum. Okay. My question is, if I give any arbitrary sequence, not necessarily a sequence which is a linear combination of eigensequences, just very arbitrary sequence, what can I do then? Because directly eigensequences are not coming. So, what can I do then? Here I will show you something very interesting. That suppose I take A, like I was taking a to the power n, I take A to be a constant, a complex value, complex constant e to the power j omega, that is a complex number with magnitude 1, phase omega. Okay. Magnitude 1, phase omega. So, in the z domain in a complex plane, if you have a unit circle, that is circle with unit radius, this will be this angle omega. So, this is e to the power j omega. This much is cos omega, this much is sin omega, cos omega plus j sin omega. If I give that as input, that is e to the power j omega whole to the power n, which is nothing but e to the power j omega n, if I give that as the input to a linear and shift invariant system, my y n, what will be y n? Y n will be, I know from this one eigenvalue times e to the power j omega n only. But what is that eigenvalue? I have to carry out this sum, where a is e to the power j omega. So, this sum will be h r e to the power minus j omega r. All right. You see h r a to the power minus r, a is e to the power j omega, so e to the power minus j omega r. This quantity will be a function of omega. So, I could write this as some lambda omega or something, that is the eigenvalue function of omega, because r is a local value variable, you are just putting various values of r. So, it is not a function of r, it is a function of omega, but we give a different name to it. We write it as a function of e to the power j omega and write in capital. If it is small h, it is capital H. Now, you see actually it is a function of small omega, because E is a constant, E is a universal constant exponential, j is square root minus 1, is a universal constant. So, if you have to plot it, you can plot only versus omega, but instead of writing as a function of omega, we write it as a function of e to the power j omega, just to emphasize the fact that in the definition of this, that is this expression, we get a series, you get a power series e to the power j omega r minus j omega r. So, e to the power j omega, e to the power j twice omega, e to the power j thrice omega, e to the power minus j omega, e to the power minus j 2 omega, e to the power minus j 3 omega. So, various powers of e to the power j omega come. It is a power series. This summation is nothing but a power series of e to the power j omega. Just to remind us of that fact, we write it as a function of e to the power j omega, but actually it is a function of this omega only. And what is small omega? Its unit must be just an radian, because n has no dimension, and this omega into n must be an angle, radian. Since n has no dimension, omega must be radian only. So, omega is called a digital frequency, as I told you the other day. Analog frequency, radian per second, we denote it by capital omega, radian per second, because there omega into t comes, t has a unit second. So, omega per second into second, second cancels, whole thing becomes an angle radian. Here n has no dimension, no unit, is dimensionless, that is why omega has small omega must be radian only. So, product is radian. Okay. This omega is called digital frequency. Fine. So, there is nothing new that has come up so far. I am giving e to the power j omega n, output I am getting again that eigenvalue written in a different form using different symbols, capital H e to the power j omega into same sequence e to the power j omega n. This sequence, by the way, this h e to the power j omega, which I rewrite this is called discrete time transform, that is dTft of this sequence H n. Okay, we just give a name, discrete type Fourier transform. Okay. In fact, this is related to the analog Fourier transform. That is, if this sequence H n or H r has been obtained by sampling an analog function, then the Fourier transform of that analog function, analog Fourier transform, and this discrete type Fourier transform, they will be related. Okay, that we will see later. Fine. Before I come back to this linear shift invariant system, I will see one nice thing, that suppose this is given to you, capital H e to the power j omega dt f t is given. Can I from this recover these samples H0, H1, H2, HR, HK, HL, HM, the samples? Answer is yes, I can recover. Fine, how to recover? Suppose I want to recover Hn for some n of my choice. That is, you ask me, get me a small Hn from this discrete time Fourier transform. What I do, left hand side, right hand side, both I multiply by e to the power j omega n, left hand side, right hand side, which means LHS becomes RHS becomes okay. E to the power minus j omega already there, e to the power plus j omega n plus j omega n. No problem. Then suppose I integrate this over a period minus pi to pi with respect to omega. So, here also I have to carry out integral. This is a function of omega over omega. Now, as I told you, integral is one summation and inside another summation. Double summations, whenever you come across in DSP, next step is to interchange them. Interchange the two summation means what? I told you the other day using discrete case, that suppose you have got one function f I comma j. You suppose I equal to a finite range 1 to 10, j equal to say 1 to 5, and you are adding. Okay, you can easily make it minus infinity, infinity, minus infinity, infinity, but just for explanation purpose, I am writing this. What does this summation means? Every time you fix a I, say equal to 1, put that here, f first coordinate 1. Then take j equal to 1, f 1 comma 1, j equal to 2, f 1 comma 2, j equal to 3, j f 1 comma 3, like that, f 1 comma 5, add them, get a result. Next again change I 2 from 1 to 2. So, f of 2, then 1, f of 2, 2, f of 2, 3, f of 2, 4, f of 2, 5, add them, get another result, and proceed like that and add all of them. This is the meaning of this summation. But you see, it is like this, I and j, I 1, 2, 3 dot 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 say 10, and j 1, 2, 3, 4, 5. So, here I means I 1, you first pick up j equal to 1, j this, okay, 1, then 2, 3, 4. So, 1 comma 1, 1 comma 2, 1 comma 3, 1 comma 4, 1 comma 5, then again 2 comma 1, okay, 2 comma, like it means 1 comma 1, 1 comma 2, 1 comma 3, 1 comma 4, 1 comma 5, then 2 comma 1, 2 comma 2, 2 comma 3, 2 comma 4, 2 comma 5, dot 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 dot. In this summation, it means first you add this column, that is I is fixed at 1 from outside, j is moving. The second comma is j, I am writing in the form I comma j. So, first point is first value is I, second value is j. So, first I is kept fixed at 1, j is varying. Then again I move to 2, j is varying 1, 2, 3, 4, 5. So, I add this column, then this column, then this column, and then I add those individual results over I. So, I am adding over j first for one I am adding over j again over another I am adding over j again over another I, and then these individual values summation results I add over various i's, that is I add the results. That is the meaning of this. But I will get the same thing if I add like this row, then this row, this row, this row, this row, and add the results over this j axis. That means I fix j equal to 1, I 1 1, then I 2, then 1, then 3 1, 4 1 up to 10 1. So, I is varying, j is fixed, I sum. Then again I move j to 2, then again I is varying 1, 2, 3 up to 10. Then I move j to 3, again I is varying 1, 2, 3 up to 10. So, I add this row, this row, this row. So, every row means j fixed, second coordinate is fixed, second value, first value is moving, that is I. Second value is fixed, I is moving. That this is what is meant by interchanging the summation. That is, first you fix j, so j equal to 1, then move I. Okay, j equal to 1, move I over this entire range, get this summation. Then take j equal to 2, put the 2 here, 2, 2, 2, and then I equal to 1, I equal to 2 up to 10, get this result. And then add all of them over j. You will get the same result, because all these values are to be added. Function f of 1 comma 1, f of 1 comma 2, f of 1 comma 3, f of 1 comma 4, f of 1 comma 5. Okay, you can put, if you want, you can put an f here. So, either you add these columns, function f of 1 comma 1, f of 1 comma 2, 1 comma 3, 1 comma 4, 1 comma 5. That is I fixed, j varying. Finish this column, hold the result. Then change I to 2, f of 2 comma 1, f of 2 comma 2 up to f of 2 comma 5. So, j is varying, I fixed at 2. Again hold the result. And these results you then add over I, because this is the I axis, I 1, I 2 like that. That was here. You will get the same thing if you add this way first, f of 1 comma 1, because purpose is to add all these values. So, either you scan like this and complete all the points, or scan this way, complete all the points. If you scan this way, that means first j is fixed, I is varying, then another j, I is varying, another j, I is varying. That is what is happening here. You will get the same result. All right. So, here it was discrete summation. Now, it could have been from minus infinity to infinity. Same thing. Any limit, you understand this logic is same. Then it can be between two summations. One is continuous integral from some limit to some limit, and maybe minus infinity to infinity, and a discrete sum, some limit to some limit. These two also sums, so they can be interchanged by the same philosophy. And in DSP, wherever you come across double summation, take my word, very next step is you interchange the two summations. Then again next steps will follow. So, here I have got double summation. After I multiplied both sides by e to the power j omega n, then I am integrating from minus pi to pi with respect to omega. I have got double summation. I take this inner summation out and outer summation in. Outer summation is with respect to, this is integral with respect to omega. Only e to the power j omega n minus r, this contains omega. H r does not contain omega. So, H r does not have to be within integral, it can be taken out as common. Only here, and this is summation over r. Now, look at this summation. From outside, r is changing, r is fixed. No, r is not fixed, you are moving r. Okay. For every r, you are carrying out this integral, obtaining the value. Then again another r, putting that r here. Okay. N is already fixed, n is your choice. You wanted to find out h of n for a particular n. So, n is your choice. R every time fixed from outside, that h r times this integral, put that r here, n is fixed, carry out the integral. And then another r, put that r here, do the same thing, and so on and so forth. Now, as r varies from minus infinity to infinity, it will become equal to n, that is r equal to n once, and all other occasions it will never be equal to n. So, r equal to n case I separate out. When r is n, n minus n 0, it is equal to 0, 1. So, then I have got this integral equal to h r equal to n, this term I am writing separately, minus pi to pi, this is already e to the power 0, 1. So, just d omega, and remaining sum or as before minus infinity to infinity, but right or not equal to n. It is moving over the range, but only it does not take this value, and this integral. Now, since r is not equal to n here, n minus r will be an integer, positive or negative does not matter. E to the power j, you can call it k. So, it will be e to the power j omega k. E to the power j omega k, if you integrate over minus pi to pi, it will be 0. Why? E to the power j omega k means cosine omega k plus j sin omega k. Cosine omega k will have k number of full cycles from minus pi to pi, that is over a period of 2 pi. You can easily see it. Directly you can work out some k, positive or negative, minus pi to pi. If you work out the integral, what is the integral? J k e to the power j omega k, omega pi and minus pi. Now, it is about j pi into k, it is about k pi what will be this? E to the power j theta minus e to the power minus j theta. So, 2j sin k pi by jk, jj cancels. But what is sin k pi? K is integer, either positive or either, I mean positive or negative does not matter. If it is negative or minus will go out, but if it could be even or odd. But sin of even number into pi or odd number into pi is always 0. Sin pi is 0, sin 2 pi is 0, sin 3 pi is 0, sin 4 pi is 0. So, this is always 0 for any k. Actually, what is happening? E to the power j omega k means you have got cosine omega k plus j sin omega k. Each of them, cosine omega k for that matter, it is periodic over k over a period of how much? 2 pi. That is, if you have k plus 2 pi, you have got cosine omega k plus omega into 2 pi, cosine omega into 2 pi plus omega k, sorry, I am writing wrongly, it will be suppose cosine omega k, okay, plus, so it will be periodic over what? If omega is changed, is omega is moved to omega plus 2 pi, that is omega changes, it is periodic over omega. If omega changes by 2 pi, so it will be omega k plus 2 pi k, but that is same as cosine omega k. So, this is periodic over omega over a period of 2 pi, same is this. There is over a period of 2 pi, it will have one full cycle, and if you integrate it over one full period, it will be 0, because positive cycle, negative half cycle, positive half cycle, negative half cycle. Okay, if it is no so, now here this integral, this is cos omega k plus j sin omega k, but you are integrating over a total period of length from minus pi to pi means 2 pi, that is one period. So, this part cos omega k will have 0 value and sin omega k integral will be 0 value, all right. Okay. So, that means this is 0. So, you are left with only first term. First term will give rise to, if you carry out the integral, it will give you omega from minus pi to minus pi. So, 2 pi h n, which means h n you can get back as one by 2 pi, then this side this is called inverse DTFT, that is given any sequence h n, if you carry out this summation, you get discrete time Fourier transform, and given discrete time Fourier transform DTFT, if you carry out this integral for one n of your choice, you get the sequence sample at nth h n, it is called inverse DTFT. All right, it is not only for h n, that is the system impulse response, it can be done for any sequence including x n. It has lot of property, but I am coming to that later. But what is the implication of this? That now consider that linear shift invariant system. If I give any arbitrary xn, earlier I was given either directly eigen sequences or their linear combination. So, computation of output was fine. You do not have to carry out convolution, you can directly write output in terms of the individual eigen sequence responses, lambda a1 to the power n, lambda a2 to the power n, like that. But if I cannot have, if I do not have an xn that is a linear combination of eigen sequences, if it is arbitrary xn, then can I still use this fact? This will give me the answer. Then now suppose I have got an xn, arbitrary xn, and I have to find out yn. One way is to carry out convolution. Suppose I do not want to carry out convolution. Xn also can be written in the same manner using its discrete time Fourier transform capital X to the power j omega into e to the power j omega n. Okay, where this is by the same formula x of r e to the power minus j omega r, same thing for this sequence, which is nothing but discrete time Fourier transform dtft of xn. So, that if I bring here and all that, this carry out, I will get xn by this result, because this is true for any sequence hn, not necessarily a particular hn which is a system impulse response. So, this xn I am giving, all right. This system is also represented by a linear operator, linear shift invariant operator t. So, my output yn is t working on xn, there is t working on this. Since t is linear, this constant will come out, t working on summation of these subsequences. Here omega is continuously varying, that is why we do not have discrete sum. Omega is continuously varying from minus pi to pi, we have a continuous sum. But t is linear means summation of these sequences e to the power j omega n with my amplitude capital X to the power j omega. This is the meaning of this. Sequences e to the power j omega n, amplitude is so much, capital X to the power j omega. And not only one sequence, because omega, for various omegas we have got various sequences, but omega is continuously varying from minus pi to pi, not discretely varying, not omega 1, omega 2, omega 3, it is continuously varying. But t over the summation of these sequences, the response will be same as summation of individual responses due to each sequence, which means t can be moved inside individual response, then summation. So, it is same as this comes from linearity, minus pi to pi, t will work on this. But t will work on this means this part does not depend on n, this is like the constant C1, C2. So, it will be outside, t will work only on the sequence part. But e to the power j omega n is an eigen sequence. So, its output I know, output if I give e to the power j omega n, we have worked out output will be h e to the power j omega into the same sequence. If I give e to the power j omega n as input, we have already worked it out, output will be of the same form multiplied by an eigen value which we called named as dtft. So, this part will be same as all right. So, output you can directly obtain by multiplying the two DTFTs and then carrying out this inverse DTFT of this product. You can also see yn, if it has, we write like this, if it has its own DTFT this, then I know what is y this, but yn can be represented by again similar formula like this, 1 by 2 pi minus pi to pi you take this This yn, again take this also yn. So, if you compare these two, you will see this is same as this. It is about j omega and present, it is about j omega and present, d omega minus pi to pi integral 1 by 2 pi present. So, from here you can get that output dTft is a product of input dTft into the dTft of the impulse response or unit sample response, which is equal transfer function. In the case of analog signals, we have seen earlier that output Fourier transform of an analog system, linear time invariant system, is product of the input Fourier transform and the Fourier transform of the impulse response, which is called transfer function, all right, which is actually convolution in time domain means multiplication in frequency domain. The same thing here. This and this in time domain were small x n, small h n. You are convolved, you are getting small y n. In the frequency domain, there is in this case discrete time Fourier transform. There is digital frequency domain. Their individual DTFTs are multiplied to get output DTFT. I am stopping here. I will continue from here in the next class.